So, reinforcement learning has become a lot more popular in recent years as the excitement about machine learning in general has grown. And fortunately, there's a new package called OpenAI Gym that makes it pretty easy for you to set up test cases for reinforcement learning. So, let's actually do some hands on practice using it. First, however, we need to install Gym. So, to do that, go to your Anaconda prompt on Windows or your terminal on Linux or Mac OS, and just type in pip install Gym. Make sure you Control C out of Jupyter Notebook if that's still running first, of course. And Gym actually works better on Linux machines than Windows machines. It will allow you to do things like play Space Invaders and train it how to play Space Invaders and do more graphical video gamey things. On Windows, it's going to be more limited because it doesn't have the access to the graphical system, but as you'll see, we can still use it. All right, so we have at least the bare bones version of Gym installed here. Let's go ahead and start our notebook, Jupyter Notebook. And of course, I'm already in the ML course folder where my course materials are. And look for the Q Learning notebook. There it is. And let's see if it works. All right, so what we're going to play with here is what's called the taxi problem. It'll make more sense when we look at it here, but basically we're modeling a self-driving taxi that can pick up passengers at one of a set of fixed locations, drop them off at another location, and try to get there in the quickest amount of time while avoiding obstacles. So we're basically going to train our taxi on how to get passengers from one point to another in the quickest way possible using reinforcement learning. So let's start off by importing the environment that we need. We'll import the Gym package we just installed and random, give ourselves a consistent random seed so we get the same results each time. And we will make our environment called Taxi V2 that just contains sort of the rules of this game, if you will, and how it all works. We'll call that resulting model streets and then render it out so we can visualize what this environment looks like. So let's go ahead and shift enter. And there you have it. So here's how to interpret what you're seeing here. Basically the letters R, G, B, and Y there, which correspond to red, green, blue, and yellow, or something, whatever you want. Those are the valid pickup and drop off locations. So a passenger may choose to be picked up at any of those locations and may choose to be dropped off at any of those locations. Our taxi needs to learn how to get them from one point to another as quickly as possible. Now, whichever letter is colored blue is where we need to pick somebody up from, and whatever letter is colored magenta indicates where that passenger wants to go to. Okay, so remember the blue letter is where we're coming from, the magenta letter is where we're going. So in this case, our passenger is being picked up at B and wants to go to G. Now, those solid lines represent walls, so the taxi cannot cross those lines. That's kind of like, the edge of the road there or whatever. And the filled-in rectangle, that orangey yellow square, is actually the taxi itself. That represents where the taxi is. Now, when it's empty, it'll be yellow, and when it's green, that means that it's carrying a passenger. So we have this little virtual taxi game here, and we need to train our taxi how to play the game. So we have a little world here, and we've named it Streets. It's basically a 5x5 grid. And we can define the state of this world at any time with just a few things. Where the taxi is, which is one of 25 possible locations, what the current destination is, which is one of 4 possibilities, and where the passenger is, which is 5 possibilities actually. It could be at either one of the destinations or inside the taxi for a 5th possibility. So in total, that works out to 500 possible states that can describe our world at any given point. That's a manageable number there. Now, for each possible state, each one of those 500 states, there are 6 possible actions associated with that state. And we need to learn which of those actions make sense for each state, right? So for each state, we can move south, east, west, or north. We could pick up a passenger, or we could drop off a passenger. So as our virtual taxi here is exploring this environment and learning about it, we need to basically associate rewards and penalties as it does things, as it applies different actions to these different states. So we'll define those thusly. If our taxi successfully drops someone off where they belong, we'll give you a reward of 20 points. If you take a time step while driving a passenger but not dropping them off, you get a negative 1 point penalty. That will serve to make sure that we reward the shortest path over time. And if you do something bad, like picking up or dropping off at an illegal location, that gives you a negative 10 point penalty. So it doesn't have any built-in smarts to know what, ahead of time where you're allowed to pick up and drop off passengers. It has to learn that too. And as far as walls go, well, yeah, it knows about the walls. We just don't allow that to happen at all. You cannot cross a wall no matter what. That's physically impossible. All right, so let's start with an initial state. Our initial state here will just be with the taxi at location x2 and y3. The passenger will be at pickup location number 2, and the destination will be at location 0. So we encode that state as the location of the taxi at 2, 3, passenger location, and the destination location. We'll set our street state to that and render it so we can visualize it again. And there you have it. So our taxi is at that initial location, 2, 3. The initial passenger pickup location, indicated by the blue letter, is location 2, and they want to go to location 0, which is colored magenta. So basically, our taxi starting over here, it has to pick up a passenger down here, and it wants to drop them off up there. All right. So let's take a look at our initial reward table for that initial state. So here's how to actually interpret the reward table here. Now, each row is going to correspond to a potential action at this state. Like we said, there are 6 potential actions for each state. So they can move south, north, east, or west, pick up, or drop off. And the 4 values in each row are the probabilities assigned to that action. And then the next state that results from that action, the reward for that action, and whether that action indicated a successful drop-off took place. So, for example, you can see that moving north from this state would put us into state number 368. It would incur a penalty of -1 for just taking up a time step, and it does not result in a successful drop-off. And initially, our probabilities are all 1.0 because we haven't learned anything yet. Let's take care of that. So let's actually do some Q-learning here like we talked about in the slides. First thing we need to do is to train our model. So at a high level, we're going to train 10,000 simulated taxi runs. And for each run, we'll step through the time with a 10% chance of just making a random exploratory step instead of using the learned Q values to guide our actions. So basically, we have a 10% exploration factor here that we're using to do the learning phase. Quickly walk through the code here. We start off by defining a Q table, which is a NumPy array, and that contains a 2D array that represents every possible state and action within our virtual space here and initializes those Q values all to 0. We have some hyperparameters here as well. The learning rate, that's basically how quickly we try to learn. Discount factor, these all pipe into that Q learning equation that we looked at in the slides. And our exploration rate, which as we said is 10%. And the number of epochs that we're going to train over is 10,000. So we go over all 10,000 taxi runs. We reset our virtual playing field here. And while we're not done, we'll first draw a random number between 0 and 1. If that number is less than our exploration rate, which is 0.1, then we will actually just explore a random action. Otherwise, we will just go with the highest Q value associated with the actions that are available to us, okay? So since exploration is 0.1, there's basically a 10% chance of a random number being less than that, in which case we just pick a random sample action. Otherwise, we go with the maximum Q value available to us for the actions that we have at hand. We then call streets.step to actually apply that action. That gives us back the next state that results from that action, the resulting reward, whether or not we're done at that point, whether we successfully dropped off our passenger, and some more info as well. At that point, we need to actually do the Q-learning equation. This is basically the code version of the equation that we looked at in the slides there. We're just taking a look at the current Q value, then one at the next state, and then computing the new Q value based on the Q-learning equation. That takes our learning rate and discount factor into account, and then we assign the Q table for that given state and action to the newly learned Q value. And we set our state to the next state and do it all over again until we're actually done and actually drop off our passenger. And that will complete a single run of the taxi, and then we do that 10,000 times. So this could take a little bit of time to run. Let's actually try it out. We'll click in here and shift enter and just watch it go. Not too bad. That only took a few seconds. That's pretty impressive, right? All right, so let's see what we got. So now we should have built up a table of Q values that we can quickly use to determine the optimal next action for any given state. So let's take a look. Let's take a look at the Q table for our initial state where we started from. So here you can see that the lowest Q value corresponds to the action, it's pretty close here, but it corresponds to the action go west, it turns out. So that makes sense. If you look back at our initial state, yeah, I mean, we want to go that way, right? So like we want to pick up our guy around this wall, like the only direction that makes sense is going west. So looks like it worked so far. That's pretty cool. All right, so let's actually see it in action. A cool thing about OpenAI Gym is that it kind of lets you animate what's going on, and it's really fun to watch. So what we're going to do in this block of code is actually simulate 10 different trips here. At each step, for each trip, we'll reset the street state. And we will just walk through it one step at a time, applying whatever action we learned from that learned cue table. So there's no learning that has to happen here. Now that we've already learned the optimal action for every possible state we could have in this world, we can very quickly guide our taxi through any given situation at all. So that's really the power of cue learning. Once you've learned that cue table, actually powering an AI to go through your virtual environment is super fast and super simple. And the really fun part here is that we can call streets.render to actually animate that taxi moving through as we go. So let's watch. There it goes, picking up our passenger down at the Y location, picked it up, and delivered it to G. Cool. And we're on trip number 3 now, picking up our passenger again. It's in the green box now, it's in the taxi, and got dropped off successfully. Starting again, picking up our passenger at the blue location and going down to magenta as quickly as possible. This is really fun. So again, we picked up a passenger at G, and now we're dropping him off down there at Y. Again, it took a really quick path. So this actually seems to work, guys. How cool is that? So we've actually trained a virtual taxi of how to find the quickest path between any 2 points for picking up a passenger and dropping them off at a given location. So fun stuff. We've taught a little virtual vehicle how to navigate this world all on its own. That's fun stuff, guys. You can just watch this forever. But anyway, if you want to play with this some more, I definitely challenge you to do so. So try modifying this little experimental block up here to keep track of the total number of time steps that it takes to actually get through all 10 trips. And that will actually be a useful metric as to how good our system is. Basically, if it gets through those 10 trips in the minimum amount of time, that implies that it's doing a really good job, right? So if you want to actually sample over a larger number of trips, you can remove that sleep function there to make it run faster, and that will allow you to run over more samples more quickly. So once you have that metric in place of how many steps it takes to get through those trips, you can start playing with those hyperparameters. So try to see how low you can make the number of epochs go before the model starts to suffer. Do I really need 10,000 training steps? Can you come up with a better value for the learning rate or the discount factor or the expiration factors to make training even more efficient? Can those factors influence how many epochs you actually need to get a good result? So these are good things to get an intuitive feel for and see how those values influence your resulting model. The exploration rate in particular is going to be an interesting one to experiment with. So if you only have time to play with one value, I would recommend that one. So that's a fun little example, huh? So that's cue learning in action, training a virtual taxi. And you have now actually applied reinforcement learning on a real example.